Myself Dinesh, working as Assistant Professor, Department of Physics. Dear students, in this video lecture, I am going to explain the topic interference in thin films. Dear students, in this video, I am going to brief the concept of interference in thin films and determination of path difference in reflected and transmitted system, how the two patterns are complement each other. Let us see one by one. Here, interference in thin films by the method of division of amplitudes. When a thin film of oil spread over the surface of water is viewed by white light reflected from it, a brilliant colors are seen. A similar color phenomenon is observed in case of soap bubbles, heated metal plates, etc. These colors arises due to interference between light waves reflected from the upper and lower surfaces of the film. This diagram illustrates the thin film interference in case of soap bubble. Here this diagram illustrates the thin film interference in case of oil. Here this CD, compact disc, the interference, you can observe thin film interference in case of compact disc. You can see the brilliant colors. Let us see the interference in thin films by reflected light. Here, let a ray of light, monochromatic light PQ, which is obliquely incident at angle I on a thin transparent film of thickness T and refractive index N. At the point Q, it is partly reflected along QM and partly refracted along QR. Similar reflections and refractions occurs at the point R and T. Thus we get a set of reflected rays. See here, in this diagram, that I is the angle of incidence and R is the angle of refraction and N is the refractive index of the medium. Here this R indicates the angle of incidence inside the film. Let PQ is the incident ray, QR and RS are refracted rays, QM and SN are reflected rays. Here RA and TB are transmitted rays. Let the ray QM and SN are obtained from the same incident rays and are coherent, produce interference. Let SX, which is perpendicular to the ray QM, and RY, which is perpendicular to QS. Hence the path difference between QM and SN, the path difference between QM and SN is given by, that is equal to path QRS inside the film, QRS, the path QRS inside the film minus path QX in air. Therefore it is written in the form of equation, the path difference is equal to N into QR plus RS. N means refractive index of the medium, that means film. Here the path QRS means QR plus RS minus QX, let it be equation 1. Now QR is equal to RS. They travels the same path inside the film. From the triangle QRY, the cos R is defined as RY by QR. Therefore, QR equals T upon cos R. Here QR equals RS. Therefore, it is equal to T upon cos R. RY means thickness of the medium, that is T upon cos R. Let it be equation 2. From the triangle QSX, From the triangle QSX, we can define sin I. Sin I equals opposite by hypotenuse. Opposite is QX, hypotenuse is QS. Therefore, on cross multiplied, QX is equal to QS into sin I. QS into sin I, that is equal to QS means QY plus YS into sin I. This is equal to 2 into RY tan R into sin I. QY and YS means QY is equal to RY tan R. Here in this diagram, you can define tan R. Then we get QY value is RY tan R and YS value is RY tan R. Hence addition of these two becomes 2RY tan R into sin I. Here RY means thickness of the medium. Therefore 2 into T. Tan R means sin R by cos R into sin I. This is equal to 2T into sin R by cos R into sin I is equal to n sin I, because according to the definition of refractive index, n equals sin I by sin R. This is Snell's law of refraction. Therefore, on cross multiply these two, n into sin R. Sin I is replaced by n into sin R in the above equation. Therefore, we get Qx equals 2t into sin square R upon cos R into n. Let it be equation 3. Substitute equation 2 and equation 3 in the equation 1. We get path difference delta equals 2nt by cos R minus 2nt sin square R upon cos R. Therefore, on further simplification, take a common factor 2nt by cos R as common into 1 minus sin square R. Here 1 minus sin square R means cos square R. Here cos square R in numerator, cos R in denominator. One term cancelled here. Then we get 2nt cos R. Let it be equation 4. The ray QM suffered a reflection at the surface of a denser medium, undergoes a phase change of 180 degree, which is equivalent to a path of lambda by 2. That means half of the wavelength. Hence, the true path difference is given by delta equals 2nt cos R minus lambda by 2. We can add minus lambda by 2 in the equation 4. We can get a true path difference. Let it be equation 5. Let us see the conditions for bright fringe or bright light. We know that in the previous session, the path difference should be delta equals m lambda. From equation 5, we can equate this path difference with the true path difference. We get 2nt cos R minus lambda by 2. This is the true path difference. This is equated with the above equation m lambda. Then this is the condition for bright fringe, where m equals 0, 1, 2, 3 and so on. Here on further simplification, 2nt cos R equals m lambda plus lambda by 2. When lambda by 2 comes right side of this equation, then it becomes m lambda plus lambda by 2. On further simplification, we get the condition for bright fringe 2m plus 1 into lambda by 2. Let us see the conditions for dark fringe. We know that the condition for dark fringe, the path difference should be 2m minus 1 into lambda by 2, where m is 1, 2, 3 and so on. We know that the true path difference is 2nt cos R minus lambda by 2, which is equal to the path difference of 2m minus 1 into lambda by 2. Then on further simplification, we get 2nt cos R equals m lambda. This is the condition for dark fringe. Now, the interference in thin films by transmitted light. We can refer the same diagram here. We know that RA and TB are the transmitted rays. It can be shown in this diagram here that the path difference between these two rays is given by delta equals 2nt cos R. 2nt cos R. Since both these transmitted rays are not reflected at the optically denser medium, No additional phase difference or path difference is introduced between these two transmitted rays. Therefore, the true path difference should be 2nt cos r. There is no additional phase change takes place here. The true path difference should be 2nt cos r. Let us see the conditions for bright fringe. We know that the path difference should be m lambda. Here the true path difference is 2nt cos r, which is equated with this equation m lambda, that will be equation 1. Let us see the conditions for dark fringe. We know that path difference should be 2m minus 1 into lambda by 2. We can equate this one with the true path difference 2nt cos r. We get 2nt cos r equals 2m minus 1 into lambda by 2, let it be equation 2. Hence, from the equations 1 and 2, it is clear that the conditions for interference due to reflected and transmitted systems are quite opposite. Hence, in the transmitted and reflected system, these two are complement each other. Let us see, the reflected and transmitted systems are complementary. It is evident from the relations derived that for the brightness and darkness of the film in the reflected and transmitted system, that the conditions of interference for the two systems are quite opposite to each other. A bright fringe in the reflected system will be dark fringe in the transmitted system for the same path difference and vice versa. Third one, thus the two systems are complementary. That means the energy that is absent in the dark fringe in the reflected system appears as energy in the bright fringe in the transmitted system for the same path difference. Hence the conservation of energy. Let us see the problems on this topic. First one, a parallel beam of sodium light of wavelength 5890 into 10 raised to minus 10 meter is incident on thin glass plate of refractive index 1.5 such that angle of refraction in the plate is 60 degree. Calculate the smallest thickness of the plate, which will make it appears dark by reflection. Here the data here. Conditions for the darkness is 2nt cos r equals m lambda. This is the condition for dark fringe. For the least thickness means m equals 1, 2, 3, 4 and so on. For least thickness m should be 1. That should be equal to 1. Therefore, the formula is 2nt cos r equals lambda. Here for m we can substitute 1. We get this is equal to lambda. Therefore, t equals, here in this problem he has to calculate the thickness of the plate. Therefore, thickness of the plate T is equal to, here on cross multiply this one and reformulated, this becomes lambda by 2n cos r. By substituting the lambda 5890 into 10 to the power of minus 10 divided by 2 into 1.5 into cos 60 degree, this becomes 0.3 into 10 raised to minus 6 meter or 0.3 micrometer. This is the thickness of the plate. Let us see the second problem. A thin layer of colorless oil is spread over water in a container. The refractive index of oil is 1.4. If the light of wavelength 640 nanometer is absent in the reflected light, what is the minimum thickness of the oil layer? For this one, let T be the thickness of the oil layer spread on water. For minima, condition is 2nt cos r equals m lambda. For minimum thickness, we take n is equal to 1. Therefore, minimum thickness T equals lambda by 2n. Lambda by 2n. This is 600 nanometer divided by 2 into n. N is 1.4. Therefore, on further simplification, we get to 214.3 nanometer. That's all. Thank you.